from in person or Zoom, any problems we need to deal with first on this chapter or anything for that matter?
No, I think I'm good.
Okay. Okay. All right. So we're going to look at chapter 12, and this is from the review document version 2. All right. If the reaction is first order in H2O2, look at that equation. H2O2 plus 3 iodine ion, 2 protons, yield triiodate, and 2 waters. And when we write the rate law for this equation, we're typically concerned, we could write it any way we want, but most of the time we're concerned with the reactants because we look at the reaction at the very beginning when there's nothing to speak of on this side to give us a opposing reaction. So we want to write the rate in terms of these factors. We have a rate constant. We have the concentration of that to some power, and then times the concentration of that to some power, and then the concentration of this to some power. I think I use P. O can get confused with an actual order. Okay, so these are the orders, and the problem tells us that H2O2 is first order. So you don't have to write the 1 in there, but the answers are given with the ones where as selections, so that there's no mistake. Let's see, iodide is second order, right? So we put a 2 here. And what is hydrogen's? 0 order. All right. So the mistake that most students make is to pick the answer that has this one in it. But if that's 0 order, what's that equal to?
No.
1. So you leave it out. Right? So actually, the one you're looking for is that, which would be, I think, the last one, E. And if you do it this way, then if I'm sneaky and I change the the orders, then you can just plug them in there and look for the answer. All right, number 2. Let's see, a reaction has the rate law, A squared B C squared. Okay. Okay. This is second order. This is first order. Yep. And this is second order. Okay. What's the overall order? This is the order with respect to that reactant or component. Order with respect to that one's 1, with that one's 2. Overall.
You just add them together, right?
2 plus 1 plus 2 equals 5.
Okay.
Yep. No big mystery there.
But how do you know B is 1? Because it just doesn't have anything.
Right.
How would you know?
It's understood. If it's there, it's got to be at least 1.
At least 1?
Yeah.
Okay.
If you're given a reaction like
Because even if it's 0, it's 1.
mhm.
Okay, I get it now.
Yeah, if this were actually 0 order, then that wow wouldn't even be there.
Okay.
Yep. Then the order would be 4. Okay, I'm gonna skip this one. This one takes a little bit too much time. We'll get another one like it in a minute. Okay, number 4. If the reaction 2HI yields, I bet it's H2 plus I2, is second order, which of the following will yield a linear plot? If we're saying it's second order, we're going by the convention that we're going to look at this one right here. So we can say the rate equals K times HI to the second power. Okay. All right, so what will give us a straight line? If we plot, if that's second order, and we plot against time, just the raw data, we're going to get a curve. It's second order, right? This is 0 order, correct? That's 0 order, right? First order is what? Natural log of HI, right? That's not first order, so we're going to get another one like that. But if we plot the inverse, we're going to get a straight line, okay, with a positive slope. Oh, okay, so that's B. Plot the inverse of HI versus time and you'll get a straight line. And that's what you do with your data. You take your data and plot each way and find out what order it is. All right, number 5. Which of the following statements about enzymes is incorrect? What's an enzyme? It's sometimes say biological, let's keep it chemical, biochemical. Catalyst. Took me a second. All right. But it has some special differences with inorganic catalysts. Right? Enzymes do increase the rate, right? They do increase the rate of reaction. Okay. But they also control reactions. Whereas inorganic catalysts, they work the same forward and backwards. It doesn't matter. They don't care. But enzyme will catalyze the reaction in one direction and not so much or not at all in the reverse. There are a couple of exceptions that are troublesome, right, in the biochemistry world, but as a general rule, you need 2 enzymes to go forward and backward. Okay, so they're usually proteins that catalyze specific biological reaction. Yep, A is true. We're looking for the false one. B, they are equal in the inorganic catalyst inefficiency. That's false. Enzymes are orders of magnitude more efficient than inorganic catalysts. Much, much more efficient. You may have to put 10–20% catalyst in the reaction mixture to get something to go inorganic, and just a fraction of a percent enzyme will make the reaction go. I mean, it'll happen like that. Okay, so B is the false one. The others should be true. Several thousand are now known. Yeah, at the time this question was written, that's true. Probably more than that by now. Molecules they react with are called substrates. That's also true. Yeah, substrates. we would call them reactants. The biochemists decided that we need a different name, so they call them substrates. So B's the only one that's wrong in that. All right, let's see. How about number 8? I don't even know. I don't remember if we talked about this one or not. Free radical? Maybe we talked about it last semester. What's a free radical? A free radical is anything. It can be an element, it can be a compound, it can be an ion. As long as it has at least one unpaired electron, that's a free radical. So, a free radical is a chemical species that possesses what? An unpaired electron, D. Free radicals, they're not too common on the surface of the earth. We get them in our bodies, right, as a consequence of chemical reactions. And they're very reactive. So they can cause damage to a cell. The kind of damage you don't want is damage to your DNA. So there are a number of dietary supplements or food products that are advertised as being free radical scavengers. And that they are usually molecules that have double bonds. They have that pi system which is kind of makes the electrons out there a little more available. They're outside the axis of the bond. And those tend to scavenge free radicals. So that's why polyunsaturated fatty acids are good for you. One of the reasons. And why vitamin C is good for you. It has some double bonds and it's a good scavenger. Okay, so the answer is D, unpaired electrons. Okay, a rate expression. Number 9, is it? Number 9. A rate expression for a particular reaction is AB squared. Rate is K, A, B. Okay. First order, second order. Okay, if the initial concentration of B is increased from 0.1 molar to 0.4 molar, so if we say one equation, one reaction, we have B set at 0.1 molar. And then, let's see, that's 1. And then we do the reaction again, only this time we increase the concentration to 0.4 molar. How is that going to affect the rate? You want to look at not the numerical difference, but the multiplier. How many times bigger is this than that? So we got from there to there by 4 times. Okay, that's the effect that it's going to have on B in here to that power. Okay. So the rate is going to be increased by 16. 16 times as fast. We sort of alluded to that during the lecture when we looked at the effect of zero order, first order, and second order on exactly the same reaction. We just changed order and saw that the remaining reactant after a certain period of time was a whole lot less for second order than it was for first order than it was for zero order. And this is another way of expressing that. When you have second order, you're going to square the speed of the reaction by the increase in B. If it was A, it would just be 4 times, right? Because it's to the first power. Well, how about zero order? If we had a zero order factor, that's not even in there. Right? If we wrote the reactions as A plus B plus C, but we said C is zero order, so it's not in the rate expression. It's independent of the concentration. So if you say we increase the concentration from 0.1 to 0.4 for a zero order reactant, then the rate's going to be the same for both of them. It's 9. Let's scroll it a little bit and get 10. All right. For which order reaction is the half-life of the reaction proportional to 1 over K? All right. So we got zero order, half-life. I don't know if I can remember all of them. The expression. I know this one. 0.693 divided by 2K, I think. Let me look. It's in useful information. So you don't have to memorize it either. There we go. Let's see, half-lives. Oh, just K, not 2K. All right, how about this was first order. And we want second order and zero order. So zero order is A over 2K. Right? Yeah, A over 2K. So this would be whatever the concentration here is over 2K. And the other one is, the last one is 1 over K, A. 1 over K, A, zero. Okay. So the question is, for which order reaction is the half-life of the proportional to 1 over K? If we factor out the K value, right, this would be the same as that, correct? This would be the same as that. And this would be the same as that. So they're all proportional to 1 over K. I think I mentioned that in the lecture, but it bears repeating. So the answer is D, all of the above. All of the half-lives are proportional to 1 over K. Right? Go. Number 13. Of the following choices, which type of collision is most likely to be the rate determining step in a proposed mechanism? So what do we have? We have unimolecular. I'll write it that way. We have bimolecular. And we have termolecular. Okay. What do we mean by unimolecular? There's only one reactant. Right? It doesn't depend on anybody else. Just the energy that's in the system, that reactant changes or decomposes, whatever. This one requires 2 reactants. It's a little less probable to get 2 reactants together with the right amount of energy and what else? The right orientation to break the bonds, form the intermediate, and form new bonds. Has to be oriented correctly. So the probability for this one is less than that one. How about this one? This one has 3 reactants. It's that if an elementary step in your mechanism is termolecular, which is very rare, but maybe you're forced to use that because nothing else works, then this is going to be the rate determining step. It is absolutely the slowest step in your mechanism, without a doubt. So that's why C is the answer. And it's purely has to do with probability. 14. Let's see, we're going to decompose some hydrogen peroxide. And it has the mechanism. Instead of writing the mechanism up here, let's just look at look at it on the board. Okay, we got these two steps. The first step takes one of those hydrogen peroxide molecules and reacts it with iodide ion. Makes water and iodate ion. Then the iodate ion reacts with the other hydrogen peroxide molecule, because the balanced equation says there are two of them. So it reacts with the other one and produces water and oxygen and releases the iodide ion again. Okay. So what's the catalyst in that reaction? It's the one that comes in one end and goes out the other. Looks like it didn't even change. Right. For the overall reaction, it's not even listed. If we write, well, I am going to write it out. If we write the equation out, this decomposition gives us water and oxygen. If we do put iodide in there, we put it here. It's not considered in the overall reaction, but it is part of the mixture and it does accelerate the reaction. But it's like that, had that video with the decomposing hydrogen peroxide and the blue dye, and it shot out the top of it. Was that in our lecture? It wasn't. Maybe I only do that one for the introductory course. I ought to put that in our lecture. Okay, so that's the catalyst. The iodide ion is the catalyst. Okay, while we're here, what is that? Because it's not in there either. This is an intermediate. Right? It doesn't go in the front and come out the back. It appears in the mechanism and disappears before it's over. All right. I don't think we talked about that in class. No. Maybe it may have been on the energy diagram, right at the very top. I don't know. No, because this is a mechanism. Right? I don't think we mentioned it. I mention it now.
Glad you informed us.
Okay. Okay. Now we've got initial rate data for these 4 experiments. What's the order of the rate law with respect to the manganate ion? Okay. So the way I do this one is I write out the equation. Let's see, this is number 17. This is going to take a few minutes. But I write out the equation, 2MnO4 4 plus 5 C2H2O4, is it?
H and C backwards.
H comes first. That's right. This is oxalic acid. I think. There we go. And then we have some these. And that's as far as you need to go, because that's all the data we have. And over on this end, we have a column with the rate of the reaction. But underneath each one of these, we have concentrations. Actually, that should go here. And here. So we have these 4 reactions, and our initial concentrations are given for each reaction, and each reaction produces a different rate. Well, most of them do. Looks like the last 2 are the same rate. Okay, so we've got this experiment. number 1, 2, 3, and 4. And we have 1 and 2. 1, 1, 2, 2 times 10 to the minus third. So what are the units here? They're all molar. This one is 1122. Oops. It's 2. This is 1122. Minus 3? Yes. See if I got it right so far. Yeah. And then this one is 1, 1, 1, and 2. Molar. 1 molar acid. That's pretty strong. This is an aggressive, an acidic solution. And then the rates, 2 times, oh, the rates, actually we're given the units. Molar percent. 2 times 10 to the minus 4. 8, 6, 10 to the minus 4, 10 to the minus 3, and 1.6 times. Okay, so there's all our data. And you'll notice that we have 3 components here and 4 experiments. That's the minimum amount you need. You need 3 or n plus 1 number of experiments to cover all possibilities, where you're holding 2 of them constant and let the other one vary. So that would be, let's see, if we hold this one constant, these 2 constant, this one varies. And that's probably the one we're after, MnO4, yeah. So we're going to use experiment 2 and experiment 1 to find out what that value is. Okay, the way you do it is you ratio. You write out the rate law. And the rate law is simply going to be rate equals K times that, times that, times that, without the coefficients. Okay. So we're going to ratio experiment. And you can do them any way you want, but I like to do them in such a way that the ratio of the rates give us a whole number, not a fraction. So in that case, we put experiment 2 on top of rate of experiment 1. So this experiment 2 over experiment 1, right? And what we get now is the rate 8 times 10 to the minus 4 divided by 2 times 10 to the minus 4. Units cancel. And then experiment 2 is going to be what? It's going to be the first one, 10 to the minus 3. And 1 times 10 to the minus 3 and 1. And then the first one is 1 times 10 to the minus 3. And these are unchanging. Okay. Okay. So now, this explains, I think, why we keep these constant while this one varies, because these are going to cancel out. Those are going to be 1 and 1. Okay. And we get an actual value for this one, which is 2. Right? And what's this one?
2.
Oh, excuse me. I left out the K, didn't I? It's going to cancel, but I should, for completeness, I should put a K in there for each one. Those K's cancel also. So this is going to be 4, right? 2 into 8 is 4. So, oh, I left something else out. Got to have that. Now, before, you would have had an M over this one and M power of that one. But math says that you can divide these two and take them both to the same power. Okay, so this is going to be to the M power. Those are one, that's one still, this is one. So what does M have to be to give you 4 from 2? M equals 2. Right. Square the 2 and you get 4. So the answer is C, 2, for the order of this one. We could do the same thing for the rest of them. Back while we're here, let's see if we can do this quick and easy. Erase that, that. And if we want to get at this one, we want to let it vary and keep the other two constant. So these two are the same, these two are the same. So we would do 3 and 2. Correct? 3 and 2. So 3 is 1.6 times 10 to the minus 3. And 2 is 8 times 10 to the minus 4. Then these values here are 2. This one is 2 on top. Right? Because it's experiment 3. 2 on top. And this is still 1 and 1. So this one's going to be 1. That one's going to be 1. What's 8, 10 to the minus 4 divided into 1.6 times 10 to the minus 3? The easiest way to do that is to convert this, make these powers the same. So this is the same as 16. 16 times 10 to the minus 4, right? So 8 into 16 is 2. And this one is 2 to the n power. All right? Haven't lost you, haven't? Okay. So the power n has to be 1, right? So this n is equal to 1. All right. Now we can do the last one. I don't want to just keep going. Get the whole rate law. So that one. And let's see. Now we want the experiment that lets this one vary and these two hold the same. So that's 4 and 3. It's 4 and 3. And that's 1.6 times 10 to the minus 3. And 1.6 times 10 to the minus 3. And these are still going to be 2 and 2. These are going to be 2 and 2. And these are going to be 2 and 1. So that's going to be 2 to the p power equals what? Because that's 1, 1, and 1. This is 1. Okay, so p is 0. So this one is 0. And it's not even going to appear in the rate law. Now we can save ourselves all this calculation. All you have to remember is, let me see, hold on a second. Yeah. Before I speak. No, yeah, do it. Yeah, be complete. That makes more sense. I was looking for a shortcut, but I think I probably muddy the waters if I do. So we found the order of protons to be 0. Right? Because this ratio of 4 to 3 is 1.6 and 1.6, that's 1. And these are constant, or cancel. And this is 2 and 1. 2 and 1. So that gives us 2 to what power equals 1 is 0. So we found the orders for each one of our reactants here. All right, let's see. Okay. That one coming up might be redundant. Let me see. Is this third? And we're at 18. Good. The rate law for this reaction is NO squared times O2 to the first power. What happens to the rate when the concentration of oxygen triples? All right, so this is the same as that one before. Since oxygen is first order, if you triple the concentration, triple the rate. Right? It's 3 to the first power. All right. We're not going to do that one. The numbering's wrong. Questions 8 and 9. I'd say 19 and 20. Well, let's do it anyway. I think it's important enough. So when we look at that diagram, the axes are not labeled, but we're told that it's an energy diagram, potential energy diagram. So we know that this is energy and this is progress of the reaction. All the reactants start at energy level here. We got to add energy to get them to the activated complex, and then they end up with reactants there. So which letter shows the activation energy without use of a catalyst? Without use of a catalyst would be from here to here. And that's letter A, correct? Yeah, A. Okay, so that's 19. Oops. That's 19. How about 20? 20 is asking for the activation energy with a catalyst. Okay, we have to draw in catalyst reduces the activation energy. But we end up at the same place we started. It just takes less energy to get there. All right, so this is use of a catalyst. Which would be which one? E, right? Okay. What is what's D? D says from here to here. D is equal to enthalpy of the reaction, right? Reactants, products. So if we have more energy in the products, we subtract less energy from the reactants, we get a positive number. This is an endothermic reaction. Those are the main components. Let's see. I don't see any others. The rest are kind of in there to confuse. Okay. Wait a minute. Am I getting some? That's a repeat right there. That's a duplicate. Okay. Here we go. Let's do number 24. Okay. What fraction of a reactant remains after 5 half-lives of a first order reaction? Well, there's blue smoke in this question. Doesn't matter what the order of the reaction is. If you go a half-life, there's only half left over. Right? Okay, so if we go 5 half-lives, you can do it this way. So after the first half-life, you have a half left. Right? After the second half-life, right, you have quarter left. So that's 1, that's 2, 3, 4, 5. So we do another half-life. That's an 1/8 left. Okay. We do another half-life. Right, we go from here, here. That's a 16th left. And if we keep going to the 5th half-life, that's a 32nd left over. So 1/32 is left. Now that's the visual way to do it. The mathematical way is 1/2 to n. And n equals the number of half-lives. So 2 to the 5th power is 32 and 32nd. Okay. Either way works. Uh, 25, right? 25 is based upon the reaction 2A sub 2 plus B sub 2 yields 2C. Following mechanism is proposed. So we have a fast step where A sub 2 and B sub 2 get together and make an intermediate R plus a C. And then that R reacts with another A2 and makes another C. So if we add them together, we get the overall equation because the R's cancel. So what's the question? Which step is the rate determining step? Has to be number 2. That's the very slow step. If you had one that said you have 3 rates, you have moderate, slow, and very slow. Very slow is the rate determining step.
So it's always the slowest one?
It's relative, right? Right. It could be a reaction that takes place in 3 milliseconds, or it could be a reaction that takes 5 years. Right? It's all relative. When you propose a mechanism, the slowest one determines the rate, and it's the source of the rate, the overall rate expression. That's, you start with that one, and you produce the overall rate equation from that equation plus all the others. And that's how you check yourself to see if your mechanism, well, one of the ways of course, you add them together and see if it comes to the overall, and then you generate the rate expression that you determine the rate experimentally, and then use your mechanism to construct a rate equation from the steps. And if they're jive, then you're pretty sure that you're on the right track. All right. So let's see, 26. For this reaction, A yields products A0 6.4 molar. 6.4 molar. And the first 2 half-lives are 60 and 30 minutes respectively. So if we start off with 6.4, let's do it this way. We start at 6.4 at time 0. And after the first half-life, which is 60 minutes. So 60 minutes, after the 60 minutes, this is the first half-life. We get, what, 3.2 molar. Not get half. That's what we got left. And then after 30 more minutes, now our second half-life is based upon this value. T1 half. It's based upon this one. This one only takes 30 minutes. So if this is equal to 30 minutes, overall is 90 minutes. And this is going to be half of that. 1.6, right? Okay. Oh, that's nice. They tell us this is a zero order reaction. Like zero order. So if it's zero order, we just look at the zero order, find this A over 2K. T1 equals A over 2K. And we can pick either one, actually. We can pick the first one and say A0 is 6.4 molar divided by 2K, and that's equal to the half-life of 60 minutes. Okay, so that's simple. Equation in one unknown, right? K equals 6.4 divided by 2 of 60. So 6.4 divided by 120. That's 5.3 times 10 to the minus 2. C is the closest one to that one. Now, if we weren't told it's zero order, how do we deal with that? Well, we find the K for this one, and then we take this one, do it again, find the K for this one. Since we know it's zero order, it should come out to 5.3 times 10 to the minus 2. But if that didn't work, right, K is a constant. If we calculate K from these two half-lives and we get different Ks, then we knew it's not zero order. Right? And we also know that the half-life for first order is not dependent on the concentration. So since the half-life for this concentration is 60 and the half-life for this concentration is 30, we know that the half-life is dependent on concentration. It's not first order. So our only option after that is to go to second order and calculate the K. Just to be sure, calculate it with both values, both half-lives, and be sure that they match. Then look for your answer. I think we did one of those in class. In the lecture part. Let's see. All right, there's another rate law. How about this one? Ooh. Okay. Is this the Arrhenius equation? Temperature and Ks. So I'm going to look in advance to find the Arrhenius equation. There it is. Okay. So rate constants for a reaction at two different temperatures. And that's reasonable. If we change the temperature, we change the rate constant. What's the activation energy for this reaction? So we get our Arrhenius equation, and we don't have to graph it to see what the values are. We could, we were not given enough information to graph it. So we go to the integrated, actually modified integrated rate law equation. So we have the log of K log, the second one divided by the first one. And that's equal to negative, is it negative E sub A? I made a note here because I think there's an error. E sub A over R. I think it's negative E sub A over R. And then we have the temperatures, 1 and 2. That may be wrong. Let's calculate it and see. Because we know what the answer is supposed to be. So what's K2? It's 1.21 times 10 to the minus 3. And K1 is 1.38 times 10 to the minus 4. Natural log of that. Then we have, this is our unknown. And what's the R value? 8.3145. Which is joules per mole. Okay, temperature. Okay, then we have the first temperature is 30 degrees. So it's 1 over 30 plus 273. Remember, this has to be in K. And then minus 1 over, is that right? Is that a minus? Okay. 49. Second one is 49 plus 273. There we go. Now let's resolve some of these numbers. I'm going to divide that one by that one and take the natural log of it. I get 2.1711. And I'm going to leave this one alone for now. Or 8.3445 and resolve that number over there. So 30 plus 273 is 303, and I'm going to take the inverse of that one. Right there. And then 49 plus 273 is 322. I'm going to take the inverse of that and subtract it from the previous one. And I get 1.947 times 10 to the minus 4. Okay. I can divide this one into that one. And that gives me a value of 2.342 times 10 to the minus 5. And this is 2.1711. So negative East Bay would be this one divided by that one. Which would be 9.266. Okay, that must be an error. That should be positive. I think it's positive because the way these are set up, rather than putting this one first and that one second, if we put that one second and this one first, then you don't have a negative there. So, yes, that should be there. It's correct the way it's written. I think, does your copy have a negative in it? Oh,
Yeah.
well,
No, sorry, I was looking at the wrong one. I was looking at the one above it. No, the one that we just did does not have a.
yeah, the one above it has a negative.
Yeah, the one above it. The one below it does not.
Right, that's because we switched those temperatures. Okay, so this needs to be positive, 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 positive. There we go. That's correct. Now, our answer is given in kilojoules. So let's get kilojoules out of this one. All right, how many significant figures can we keep? It looks like 3. So this is 9.27 times 10 to the 4th joules. So how many kilojoules is that? Well, we can take 10 to the 3rd of these and make a kilojoule out of them, can't we? That leaves 10 to the 1st. So 10 to the 1st times 92.7, and 9.27 is 92.7, and then we have kilojoules. So 92.7 should be B. All right. 32. Consider the following balanced reaction and the experimental results that follow. What are the rate law orders for NO and H2? Okay. All right, we got 2 reactants, we got 3 experiments. That should be fairly simple. So we've got, I'm just going to write, the rate law is going to look like this. Rate equals K times NO, yes, NO to some order, and then H2 to its order. And the data we have, I'm going to work from that and just say, all right, if we want to get at this one, which ones do we have to ratio? We want this one to change and the other to stay the same.
1 and 3.
Yes, 1 and 3. Right. So experiment 3, ratio to experiment 1 equals, the rate for 3 is 2.4. And the experiment 1 is 0.6. That's equal to the K divided by the K. And then we have this value to the N for experiment 3 would be 0.03, right? 0.30. And the first one will be 0.015. 5. And then we know this one's going to be 1, right? That one, because we made sure that it didn't change. So this has, that cancels. And this is 0.6 into 2.4 is what? 4? Yeah, 4. And this is 2 to the N. So N has to be equal to 2. We have to square 2 to get 4. Right? So this N is equal to 2. How about the other one? I'll leave that one up there. So the other one we want to vary. Let's see, 2 and 1. How about that? Experiment 2 and experiment 1. So experiment 2 gives us, let's see, 1.2 divided by 0.6 equals K, cancel. This one's 1. This one has 0.4 divided by 0.020. And this is to the N. Okay, so those are gone. This is 2, correct? And this is also 2 to the M. So M has to be equal to 1. So that's 1. All right. So the orders are 2 and 1, or C. Okay. Number 33. First order decomposition of hydrogen peroxide at minus 28 degrees occurs with a half-life of 50 seconds. Starting with a concentration of 25.2, what will be the residual concentration of H2O2 after 5 minutes? Okay, I like to put this on the board. H2O2 concentration. and then time. So first half-life of 50 seconds, starting with a concentration of 25.2. 25.2 at time 0. And then after 50 seconds, that's the first half-life. We should have what? Let's see, 1, 2, 6, right? Yeah. 12.6 molar should be left after the first half-life. So we want to know the residual concentration after 5 minutes. So that's 5 times 60 equals 300 seconds. That's what we're after. Okay, what equation do we have? If this is, we're given as first order. First order. What's the integrated rate law for first order? It should be natural log minus KT over log base 0. So first order is natural log of A equals negative KT plus natural log of A 0. Correct? I'll write that right. Okay. Also, the half-life is 0.693 over K. So T 1/2 equals 0.693 over K. We can't use that equation until we know what K is. So we got to find out what K is. So the first half-life is 50 seconds, 0.693 over K. So K is simply 0.693 divided by 50. Which is 1.386 times 10 to the minus 2. Now, we can complete this equation. We want to know the concentration after 300 seconds. So this is an unknown. That's after a certain amount of time. This is our original amount, which was 25.2, right? Okay. Time is 300 seconds. And minus K, K is 1.386 times 10 to the minus 2. There we go. So we can resolve this whole side over here. Let's do that first. There are no variables left open over here. So I got that one in there. I'm going to change the sign. This one, then multiply it by 300. Okay. Then I'm going to take the natural log of 25.2 and multiply and add it to this value. So I get minus 9.3116 times 10 to the minus 1. And that's the natural log of A. So how do we find A? Right, base E. E to that power is A. Okay. Or take the anti-log of this value. Anti-log is usually listed as E to the power. At least on my calculator it is. Some of them might say anti-log. Anti-LN. So I got that one in there. I just need E to that power, which is right here. So let's see, I'm going to put it in standard notation. What's left over? 0.394 molar. Okay. So what's the trick to this one? Knowing that if you're going to find a concentration after a certain amount of time, you need the integrated rate law. So we go to that. go to the integrated rate loss. We need that. Okay, what's missing? Well, we know what this is. And we know what that is. But we don't know what that is. So that's when I had to go over here and say, we're told it's first order, so I can use that equation to find out what K is. Then we're off to the races. Let's see, 34? 34 coming up. All right. 34. For the second order reaction, NO plus O3 yields NO2 plus O2. The rate constant has been measured to be 1.8 times 10 to the 7 at 298 K, and the activation energy has been measured to be 11.4 kilojoules per mole over the temperature range 195 to 304. Okay, so we're in the right temperature range. What's the rate constant at 233 K? Let's put up here what we know. Rate constant at 298 K. So K at this temperature is 1.08 times 10 to the 7th. 1.08 times 10 to the 7th. At what temperature? At 298, right? 298. Okay. And the activation energy has been measured at 11.4 kilojoules per mole. So E sub A equals 11.4 kilojoules per mole. But remember, any equation that we're going to use where R is involved, it has to be in joules. So we might as well go ahead and change it to joules, right? 11.4 times 10 to the 3rd is 1.14 times 10 to the 4th joules. So that's our activation energy. The second temperature, I think. What's the rate constant at 233? So at the second temperature, 233, okay, we want to know what that is. So I think we're going back to the Arrhenius equation. Yeah. We need the Arrhenius equation because it has temperature and K in the equation. So let's see, can I remember this? So that's a natural log of K2 over K1 equals activation energy divided by R times 1 over T2, isn't it? 1 over T1. So I got
Supposed to be 1 over T1.
I got it backwards, so yeah, 1 comes first. 1, 2, there we go. Okay, so do we have what we need? We got this one. We got that one. We know that's a constant. We got these two. Yeah, we can solve them. So the natural log of K2 over 1.08 times 10 to the 7th. It's that side of the equation. On this side, we have 1.14 times 10 to the 4th joules per mole and 8.3145 joules per K mole. And then we have our temperatures that are already in K. So the first one is 298 minus 1 over 233. Okay. We can resolve this side of the equation. Let's do that first. I'm going to do the temperatures first. 298, take the inverse. And 233, take that inverse. Subtract that one from the first one. And you have minus 9.36 times 10 to the minus 4. And 1.14, 4 times that divided by 8.3145. So on this side of the equation, I got minus 1.2835. Now, how do we resolve this one? We have to go back to our log tricks. The log of A divided by B is the same as the log of A minus the log of B. So this is going to be log of K2 minus the log of 1.08 times 10 to the 7. Okay, so we can resolve that one. 1.08 exponent 7, take the natural log of that. This is 1.6195. So that minus, if we take that minus, right, and put it on that side, it becomes a positive, right? 1.6195. And then, oops. No. 16.195. There we go. That's what I get for using scientific notation. I ignored that exponent. So now this one is 16. And I just need to just get on this side now. So the log of K2 is equal to 14.9115. And then K2 is e to that power. So let's see. Here it is. So I get 2.99 times 10 to the 6th. Close. Closest one to that in the answers is 2.96 times 10 to the 6th. Pick the best answer. Okay. You didn't get it? E to the 14.9115 power. Is that where you're stuck? Is that a phone calculator?
Yeah.
Oh, okay.
This one doesn't work either, so.
Oh. 14.9115.
I have no idea, right there.
Okay, so what you have to do is say, push the E button, the E to the X button. E to the X button, and then put in the.
Oh,
There you go. Got it. Okay, that's 34. I assume everybody's happy with what we're doing, because nobody's stopping me. Or correcting my errors. All right, let's see. What's the next one? We'll skip a few redundant ones. And, oh, there it is. Okay. Activation energy. Okay. We just do 39, 40, and 41. 39 and 40 should be like the previous one. So without the use of a catalyst, we're looking at E, the span of reactants to the top of the red. Right? With a catalyst, we're looking at reactants to the top of the blue, which is A. That's the activation energy for catalysts. And then the last one was missing on the last conversation. Which letter shows the activation energy for the reverse reaction without the catalyst? That means you've got to go from products to the top of that red, which is C. And that'll be the activation energy for the reverse reaction. If the activation energy for the reverse reaction is huge, then the reaction in the forward direction is virtually irreversible. All right. Oh, good. Let's do this one. I think I need to shrink that a little bit to get more of it on the page. There we go. So we've got this graph. And it's a plot of the natural log of SO2 CL2 concentration over time. And this reaction takes a little bit of time to occur. Right? We've got it up to 10,000 seconds. And the natural log is in the y-axis. And we're given the equation. Right? So that equation represents what? Well, it's a straight line, but if it's a natural log against time, what order is this reaction? Let's see, this is 42. 2. The reaction order is first order, right? Natural log against time with a straight line is first order. So this is B. And 43 is looking at the same graph. What's the value of the rate constant? All right. So go to your useful information, find the integrated rate law for the natural log, which is natural log of A minus KT, natural log of whatever that is, minus KT plus the natural log of there. So with this, if we match up that straight line, this is y, this is minus 2.2 times 10 to the minus fifth, 2.2 times 10 to the minus fifth, that's this right here. Right? It doesn't matter what the rest of it is, because the question is, what's the value of K? Well, if this is negative K, then K has to be equal to 2.20 times 10 to the minus 5. Okay. And that should be B. Okay. Another B. All right. Oh. Huh? That's it. Yeah. Any questions, problems, mistakes I didn't catch? So if I were to give you a graph that plots the inverse of the concentration against time, you know that would be second order. And then you'd go to your useful information, find the second order equation, which is the inverse equals KT. And the slope of that line would actually be equal to K. And the y-intercept would be 1 over the A0. So if I ask you what A0 was, then you just have to read off the graph what that value is and take the inverse of it. And that would give you A0. Or at any time along that graph, if I wanted you to say, what's the concentration at time such and such? Then you would read off the graph what the concentration was at that time, take the inverse of it, would give you the concentration. Okay. So this is practicing how to read a graph. Okay.